really, we'll see if it goes wrong or not. Nigma, in the meantime, looking for some way to get this fight happening in their favor. I push the wave for a second. You would love for them to go in and get the next tier of items, but obviously Nigma having no access to the jungle, they can't do that.
They haven't got a single tier 4 yet, and like how can they? Like maybe PA can blur out the base, but look at Liquid's wards. They're just on the camps, seeing if anyone tries to sneak out, they'll instantly kill their opponent.
So there they go, up towards high ground. Koikva punching away. They use the, well, glyph, nothing. Tower's just down, jump forward, good call. Is it gonna be enough though? They bring him down. Miracle dead with no buyback. He didn't get anything off. Boxy pops the cheese, runs away. And now the bear going to fall, but Mickey, eyes on the prize, tearing them apart as they will lose the melee racks afterwards. Perfect execution coming out from Liquid as they find the man they needed to, get the kill, and now looking to close this one out. What more could you want?
And this is very clean play. A little bit of a departure from their performance in this TI qualifier. I'm really... Wait, what just happened?
He just kills Dark Willow with the glaives bouncing as the...
Yeah, I'm muted. Sorry. So yeah, I was saying that welcome to the stream. We're gonna have a coaching session with someone in about like 12 to 10 minutes. But in the meantime, we're kind of just like chilling out, hanging, whatever. You know what I mean? We're just gonna like hang out and have fun for a little while. I'm just kind of like on Hacker News right now, just seeing like what the fuck is in the world right now. So how y'all doing? See now. Tyrannia spreadsheets. Are syntactically valid. Oh, that one. This one might be interesting. Basics of icon design. Hot. Easy using sauce. That might be interesting. Okay, you finished. Malward says, good, I finished my intern project 3 weeks early and got good midpoint feedback. So we're feeling good about it so far. Yeah, like, it's, especially when you're an intern and you're just, like, starting out and trying to figure out how the fuck things work at a tech company, being able to get very frequent feedback every, like, day or every other day is actually really, really good. They can actually give you a lot of valuable insight into not just the flow of how we develop things, but also how these senior engineers think as well and how they evaluate problems. I think as an intern, that's ultimately the biggest benefit that you can get. Access to someone else's thinking in real time and giving you a live example, you know? It's not just like a company process because like the processes at Google, Facebook, Apple are going to be like pretty similar all around. You know, you're going to have like ship code, deploy it, you have like maybe to manage diffs or something like that. But really the value is in the people that you're going to be with. So, schizophrenia linked to marijuana use disorder is on the rise. Okay. I mean, press X to doubt, but alright. Meme stocks are mired in the longest losing run since Frenzy began. Alright, so whoever's holding GME, shout out to y'all for diamond handing that, but y'all losing a lot of money. Let's see. Like things in Hacker News right now are kind of slow, you know. I haven't seen anything interesting. Hacker News sites riddled with. Okay, news sites including Huffington Post, Vox are riddled with pornography. Okay, I'm not gonna touch that one. You know, YouTube stream and all. TikTok's algorithm figures out your deepest desires. Oh, it's a video. You might as well watch it.
Okay, has anyone else noticed that your For You page...
Oh, it's 13 minutes long, but yeah, I'll figure that one out later. But I'm pretty sure that the way TikTok works is just like it characterizes the video based on like ethnicity and a bunch of weird stuff like colors, and then just like kind of does like some really advanced linear optimization on that. So each of these characteristics are giving weights, and then based on that, everyone has an individual score. And so because of that, they will recommend you certain videos on the front page. I think the scoring algorithm is not unlike what we do in just about any other industry. So let me give you an example actually. And this is a good segue. So Uber, blog, green, what is it? Submit queue. And this is something that I've kind of just recently figured out. So actually, if you've been at a big tech company, you'll realize that there's a lot of complexity regarding being able to just simply submit your diff, because you know you're fighting with a bunch of other people who might have their diff submitted, right? So like how does this like one pipeline that's responsible for potentially hundreds of diffs per hour resolve all these things efficiently? You know, because if one thing gets merged in that breaks everything, then boom, you know, everything gets blown up. Not to mention, because the pipeline is always changing, you can't do like a synchronous block every single time. Like, you know, you test the changes, merge it in, make sure there's no merge conflicts, test the next set of changes, merge it in. Because, you know, these test cases can run like for 4 hours, the entire suite, because they could be emulated and whatever. And so, like, one of the things that Uber really did, and I think this is actually quite interesting, is that they actually do like this probabilistic modeling of whether or not they think that your diff is actually going to land. Now, this probabilistic modeling is based on a bunch of different things, like how many components in the modules in the build graph that you're going to touch. So, for instance, modules that touch like the base of everything are actually going to be more at risk, which makes sense because so many things depend on it, right? So if you introduce a change up here and 3 modules are dependent on you, then it's considered like it's higher risk than something that just has one dependency. So that's one way you could actually evaluate that risk, and then in order to prioritize which diffs that you should land first. And usually you want lower risk diffs or lower diffs that have less chance of conflict to go in first, because that way you don't have a bunch of things blocking. You could do like this optimistic land as well. But I think the biggest and most interesting thing, so here's the little graph that says the conflict analyzer and the speculation engine, is like this line here where if I can find it, it's God, where is that line? It was speculate them all. Load balancing, don't need, that's not it. That's not, oh, model training. Yeah. So one of the things that they do here, and this is talked about in like the section 7 for model training, is like not just the changes, the revisions, but also the developers themselves, you know? And what they say here very explicitly is that experienced developers do due diligence before landing their changes, while inexperienced developers tend to land buggy changes more often. And so because of this, one of the things that the model actually really does is that consequently that we selected several developer features, such as their name, employment length, and levels, in order to try and figure out whether or not this diff will actually land. So in other words, Uber's submit queue, in order to try and guess whether or not your diff is more likely to land, will actually use your job title and how long you've been working as a factor in whether or not they want to prioritize your diff. In other words, if you want to land your stuff faster than anyone else, you gotta get promoted. I thought that was like absolutely hilarious here. So, I think papers like these are actually quite interesting, and I'll bet you that most people who use the submit queue or any piece of technology at any given company, like, literally have not read the white papers on how the technology works, which is kind of mind-blowing to me, you know, because you're using this every single day. You should really actually you should really take steps to really understand what exactly is being used here, you know, and how it actually works. I find these like build graphs and these explanations for them actually very, very fascinating because this is something that I work on actually quite a lot. So for people who don't know, like when you go and run like a piece of Java code and compile it, you are more used to just feeding the Java compiler all of the files, like maybe you had a project back in the day where you just hit Java C and then you threw all the Java files at it and then hoped that it would figure it out. But at scale, that doesn't really work, because fundamentally underneath Eclipse, that's exactly what it does. But at scale, when you're dealing with millions of Java files, you can't possibly compile the entire project every single time you want to run things. You usually just want to compile just one little small segment of the code. And so this is where your build graph comes in, and modules. That these modules will contain independent chunks of code. That can be like a feature, that can be some section of the project, and then it will just compile that one little thing. Because fundamentally, these Java C compilations are just compiling Java files, right? And so the modules that you depend on are actually going to be stubbed, which means that, hey, they say these functions will be given to you at compile time when we actually go and run the entire compilation against the entire project. But for now, as we promise you that these functions and public available variables are going to be available to you, and that's like quote unquote the promise that allows you to build any one of these modules very quickly. On top of that, things like Bazel and Buck have this remote cache where these modules, what ends up happening is that they will pre-build these modules for you. So that way, instead of having to compile it on your machine, you can actually download the pre-built binary. And it's going to be the exact same as if you had built it yourself. So this also cuts down a lot on your resources being used on your laptop and also space as well. I think just the fact that this actually exists in a in this way at scale is pretty fascinating, and I think it's a great demonstration of the application of things like dependency graphs, topological sorts, in order to try and figure out what target to build. So I highly recommend that if anyone is pursuing a career in these top tier tech companies, read the goddamn white paper, because chances are, if you graduated from like college and shit, that you actually have the ability to read this. So I will link it. I'll link this in the chat, but I highly recommend anyone actually read this if in order to get a sense of like what you can do in order to try and stand out from the crowd. You walk into an interview talking about how their own goddamn system works when the interviewer does not, they will be absolutely blown away. So that's a key tip that's like a really good tip for your interview. But focus on your bread and butter, your leak coding, your system design, your ability to solve and break down problems. Once you get that done, then you can go ahead and do fancy shit like this. But I think that reading these are pretty goddamn fascinating. So, So while we still have a minute left together before I give my time over to my client, any questions from the crowd? What's my headband? So this one I actually got from a skincare shop near where I live, and so they were some of these like really cute headbands that are basically just fleece, and they're used to keep your hair back. But I use it after like I wash my hair or something like that. But honestly, I think I've shown up to every single one of my Zoom meetings wearing this. That my coworkers comment when I don't have this on. It's really nice. It's like more fuzzy. It's like cost me $10, but I think you can find it on Amazon for a pretty similar price. How are you meant to use that white paper in an interview? It's more so of understanding how these really, really nuanced products are built. So what I was really trying to say here was that if you can understand how and why these tools are built, you have a pretty good understanding of the engineering process in general. The factors to consider. What is the scope of the problem, and so being able to read this is like, and being able to talk about it just shows that you really care at the very least about the core technologies that the company is using. I think having a very key interest in just what the company is doing at an engineering level is a good sign and a great green flag for a candidate. But if you want to use it in an interview, it's more just like a talking point, but also to satisfy your own curiosity. I think that just being able to talk a little bit about this is it's something that most candidates do not do. It's just a tip that I'm giving to maybe stand out from the crowd, but also to help you in your own engineering thought process. You can also make it part of your answers to behavioral questions, like learn and be curious. Yeah, if you can go into depth about a white paper from like another company, and just say how you might have done something similar, or maybe connected to one of your own projects, I think that's absolutely massive. Especially since a lot of times, you guys are working on like, especially if you're at the junior level, you're just like kind of working on projects that are just products with no engineering guidance. Being able to relate your own projects to these things is like super, super great, I think. So, all right. So we're going to bring on our client. So hopefully you guys are ready. We're going to be doing a coaching session for 2 hours. So with that, let's bring him on.
Hey, how's it going?
Hey man, what's up?
What's up? What's up?
Nothing much. Yeah, man. So welcome to say hi to the stream for us.
Hello, everyone. My name is Christian, and yeah, this is our first session together.
Yeah. So how about this? Tell me a little bit about yourself. Tell me why you're here. And tell me like what I can do to help you.
Yeah, so I just graduated with my CS degree. I was able to complete around like 3 to 4 software engineering internships, but none of them were like big tech, a lot of mid-sized companies. So now that I'm graduated, I've made it to a couple final round interviews, but no luck yet. So I'm just ready for like that final push to be able to crack these last interviews.
Yeah. So you got to like 3 or 4 on sites, right? Did you pass them, or are you just waiting?
So I made it to 2 on-sites previously, and I didn't get offers for those. And now I have like 2 coming up, and that's why I kind of want to get coached now so that I have a higher probability of getting through those.
Right, that makes sense. New grad, you never done this before. I think the first not getting an offer from the first 2 on sites is fine. So that being said, let's pivot. Where do you think you're messing up?
I think it's my studying and the way that I'm approaching problems. So like usually when I'm doing like a leak code problem, I feel like I give up way too quickly, or I will do like what everybody does, I think, and go straight to the code when I think I have an idea, but I don't, and then I just end up writing really shitty code. Um, in interviews, I think where I fall short is like I feel like I'm good at communicating, but I get really anxious and like I second guess myself too much. And sometimes that screws me over.
Okay, yeah, that makes a lot of sense. So, yeah, okay, so you second guess. Does that mean that you don't really how to say? Are you able to solve these problems when it comes to the on-site, or is it like 50-50?
So like most of the on-sites I've been able to fully solve. But like I want to get to that point where like I just feel like really confident. Like I right now I don't feel comfortable, and I think that's why when I get to the final rounds, I'm not making it through. Because like I'm like confident when I'm like on my own and like can hype myself up, but then when I get into like these situations, I kind of like shit on myself and I'm like, let me just start second guessing everything.
Okay. Okay, yeah. So basically, that what that's telling me is that you don't have a very good approach to solving these problems, or at least it's not very refined. Um,
Yeah.
I would say that's probably your biggest cue. Now, tell me a little bit about how you've been studying. You said that, and I want to dive a little bit deeper into this. You say that you give up way too quickly. You write code very with just a simple idea, and the code ends up being shitty. do you spam the LeetCode compiler until you get an answer?
Yeah, so like lately when I'm studying, I've been trying to note as much as possible and kind of like follow that approach of like don't even think about coding anything until you like really feel great about your ideas. But I feel like if I can't come up with like a pretty unique or not unique, but like the clever idea within like 10 to 15 minutes, I give up.
Mm-hmm.
And I feel like that's been really bad on my studying on my part. Because like then I'll view the solution and then like there's sometimes where I'm like, I probably would have got that and I just like screwed myself out of a possible like learning or like situation or just bettering my problem solving skills.
So I'm gonna tell you, like right now, you're basically I would say you're almost starting from a place where everyone starts from. It's like, okay, I know how to solve some LeetCode problems, but I don't know how to like do it consistently. So you're basically starting from where I would say the base state of what I'm willing to coach. So that's good news.
Cool.
I would say that, and plus I remember you mentioning that you had like some upcoming on sites, but you can push those out to like 3 to 6 weeks.
Yeah, I pushed those up today actually.
Okay, so based on what you just told me, it's going to take you at least a month. If you recall Devin from like a stream like maybe a few like maybe a couple weeks ago, he was basically in the exact same place. But like within like 3 4 weeks, we were able to get him like an offer from Amazon. So I'm saying that it's doable, but you got to really work on this. So
Yeah.
that being said, what you just told me about robbing yourself of learning opportunities, I'm going to say that it's not impossible to learn when you look at the answer. Why? Because if you look at the answer and then you try to reverse engineer how they got the answer, then you know, okay, these are the steps I need to do in order to try and get to the answer this time. More specifically, let's say that and this is touching on what you said about not being able to know the efficient, clever solution in 15 seconds. I'm going to tell you, no one knows the efficient solution in 10 to 15 seconds unless you're a giga genius. The way you get to the efficient solution is almost always by just coming up with a brain dead, naive solution, fully understanding the problem, and then parsing it down, looking to see if there's any any patterns that you can take advantage of that are like a sub part of the problem, or there are inefficiencies that you can make better. For instance, let's say you're sorting something that's already sorted. You can skip the sorting step. Or if you're using extra memory by iterating over the same data set, then you can always like look at the data set while you're traversing instead of having to use extra memory. You know what I mean?
Right. Yeah.
So almost always your thinking should always go from very simple steps to then and then from there you make simple observations in order to build up your solution. That's why a lot of these crazy solutions can seem absolutely crazy, but it's like there's a step and a process to it. And I think that if you can get there and have a very clean, logical way of doing it, then almost always you will pass the interview. And this is for anyone who's watching as well. As long as your logical step is very clear and clean cut, and you pretty much follow that template, you're pretty much guaranteed to get all the answers. Now, where this becomes difficult is knowing how to break down the problem, and this is like basically what you're here to be coached on. Because I could just tell you this and you could go on your day, but we're here to basically train that habit here. So with that, let's actually do a problem, and then let's actually see where we're at. So
Okay.
let me share with you the link. Okay, let me open Discord. Okay, so then let's say 100. Let me know when you can edit this.
Yeah, I'm good.
Okay, cool. So let me pull up a problem and then we'll get started. Okay, so you might have seen, I don't care if you've seen this one before, we're simply just going to be focusing on your ability to parse, dissect, and solve problems.
Yeah.
So. This one, no. Okay. So, let me pull up the timer. Where's the timer? cool. Let's go. So what I want you to do is, given a binary tree, I want you to find the lowest common ancestor of 2 given nodes in the tree. So for instance, let's say I pick the nodes 6 and 2, right? The lowest common ancestor of these is going to be 5.
Yeah.
And if I pick like 6 and 8, then the lowest common ancestor is going to be 3. So.
Okay. Yeah, that makes sense. So then I'm assuming that we're just given like a binary search tree, and we're given 2 nodes that we're looking for, and yeah, like you said, we're looking for the longest common ancestor. So yeah, we can just use like a simple DFS to do this. I guess if we wanted to think about some ways to do this, maybe we can go through an example. So is that cool?
Yeah, you can go ahead and do the example. Or do you need me to supply it?
Sure. Yeah, maybe you can supply
Okay.
it. That'd be easier.
So like I said, so I'm giving you a few, like, so if I gave you the node 6, let's call it 6, and then 2, then we're going to get you to 5. Because the lowest common ancestor is 5, right? If I pick 6 and 8, the lowest common ancestor is going to be 3. So those are your examples. Let me know if you have any other issues.
Okay. No, yeah, this question makes perfect sense. So I think an approach that we can do is obviously some simple DFS on recursing on the left and right side of the tree. And I think if we were to do DFS, obviously it would be recursive, so we would need some type of base case. So if we were to think about that, we can think about like the simplest case for this type of problem. So maybe like obviously if the root is null, then we can just return. But now we can think about what about these 2 nodes that were given? And I guess we can call it like node 1 and node 2. So if we were to do a DFS on any of these nodes, we can continuously check if one of these are equal, or if the root, I'm sorry. So let me actually take a step back. So if I'm going to do a DFS approach, I'm going to first explain our base case, and then our actual recursion. So if we were to use DFS on this, there's clearly 2 cases. It's possible that we're given just a null root. So if that's the case, we can just return our root. And then our second case is kind of like when we get to a simple solution as well, is we can say if the current root that we're on is ever equal to node 1 or node 2, then we know that we can just return the root because we were able to successfully find it. So I'm just going to say that if I'll just say node 1 or node 2 equal to root, then we can just return the root because we found the lowest common ancestor. Now we can think about a little bit of the other cases, right? So it's possible that like maybe one of the sides are null and one aren't. So we would probably need some type of check for when we're doing our iteration. Or let me actually take a step back there to better explain this. So when we're recursing, we're clearly going to make a recursive call on the left side and a recursive call on the right side. So we can say that here. So we're going to recurse on left, and we know that we're going to recurse on right.
Okay.
And maybe that method looks something like, I don't know, LCA, we're going to pass the left root, and we're going to pass our node 1 and our node 2. And then our recurse on our right would be the same, but obviously recursing on the right-hand side. So after we have these variables, we can kind of think about how we can now use them to help us find the answer to the question. So another case that we can get is when left and right are not equal to null. And I believe that's in a case where we can just simply return our root. So we'll probably have to take care of that.
I'm going to
Something
put a
along.
pause here because you're talking a lot about DFS, but what purpose does the DFS solve? Like, what is the solution? What's the bigger solution that you are trying to do? Because this DFS is meant to find something, right? Well, what are you finding, and what do you intend on doing with it? What is your bigger overall solution?
Sure. So I guess if we were to go back to this example, so like if we're given 6-2, we know that the lowest common ancestor is clearly 5. So we're looking for that 5, right? So when we're recursing on the left and right, the main point of the recursion is to find basically the parent of whatever node, or ancestor, I should say, that has these nodes below it.
Okay.
So does that make sense?
You're trying to say that in a more simpler way, like a 5-year-old can understand.
So we're basically trying to find the node that has these two nodes below it.
Sure.
I guess that's a clear way to
by
explain.
definition of the problem, sure. So then, how does what you're doing get us closer to finding that?
Sure. So if we were to recurse on the left, we're basically going to ask ourselves if that given root is equal to...
when you say given root, you're given 2 nodes. What do you mean given root?
So when I'm talking about root, I'm talking about like the actual root that we're on. So like if we were to start at 3, for example, when we're at 3, we're going to check if that left side, or I'm sorry, when we're at 3, we're going to check if that is equal to either or of the nodes that we are given.
Okay.
So in this case, we see that 3 is not equal to 6 or 2. So we're going to recurse on the left side, and we're going to recurse on the right side.
Okay.
So let's say we first recursed on the right side, and we're now looking at the 1. So we know that the 1 is not equal to the 2 nodes that were given. So we can simply perform a little bit. This is where I'm a bit confused, but I'm trying to work through it.
Okay.
Of what we can do here. So when we get to the 1, we see that we have 2 nodes, so we can probably keep recursing, and we're going to end up seeing that none of these nodes are ever equal to the 2 that were given. So now let's say that we were to backtrack up to the 3 and then now visit the 5. So when we're now visiting the 5, we're asking the same question, and we see that it's not equal to 6 or 2. But when we get to the 6, we're obviously going to see that it is equal.
Okay.
So now that we know that it is equal, we would have to return the root, which is originally 5, to be able to correctly return that lowest common ancestor of the 2 nodes.
Okay.
And
so you're basically saying that if the child nodes are found at, like, say 5, like you look at 5 and you could find 6 and 2, then you found your lowest common ancestor.
right.
Okay. So then how does this work when it's, say, not the direct child? Like, say, in the instance of 6 and 8.
The instance of 6 and 8. Okay, so you're saying, like, yeah, it's not direct, that it's possible that it's even on the right side. So then for this, let's see. Oh yeah, that one's tricky. just taking a second to think. So I guess like now looking at how I approached it, so if we're seeing like if we get to this 8 first, for example, then it's obviously clear that at this point we still really don't know what the lowest common ancestor is, because with how my approach is going now, it would technically say that like 1 is the lowest common ancestor. So we have to be able to somehow know that 6 is on the other side. Yeah, I'm a little bit stumped on this problem, I'm not gonna lie.
Okay. Okay. So how are you gonna unstump yourself?
So I guess we can trying to think of. So this is kind of what I mean of like when I kind of get stuck on like one idea and I start like stressing on it, and it's hard for me to like think about another idea because I feel like I've already gone so deep into it, you know?
No, but fine. You basically just means that you aren't approaching the problem right. So let's do this. Since are you gonna throw in the towel then? Let me ask you that.
I gotta say, it's been a long time since, not a long time, but I haven't studied tree problems lately.
Okay.
So I think I am.
Okay. So basically, I'm going to tell you right now, I've already seen a lot in the first basically 5 minutes. I kind of knew that you were not going to solve this problem. Do you know why?
Probably because I immediately like went into like how we can approach it, and I started like explaining like a base case when I didn't even have like a full understanding of how DFS would even work.
Well, not just that. Yeah, that's basically it. It's not just that you didn't know how DFS even worked. It's more like, it's like you knew what DFS was and you basically had some idea of how it worked, but there was no bigger picture. There was like, you didn't solve the problem. You were just trying to write code. And then I'm like, okay, and I kept trying to refocus you into, okay, how does what you're writing service the solution that you have? Which is like, you don't have one.
Right.
So.
Exactly.
So let's wipe the board right now. I'm gonna paste my comments right here, but you can go over them on your own time. But that's basically the bottom line is that you're so fixated on making your DFS clean that you fail to even solve the problem. So so remember what I said in the beginning. We want to start off with the brain dead solution, really easy to understand. What do you think that solution is? If you had no tools in the world, no coding, what is the easiest way of solving this problem? In the abstract.
I guess like the easiest way would just be to like, I don't know, like what do you mean by like no code or anything?
Like if I said, hey, you cannot talk about this in a algorithm way, that you need to talk to me as if I'm a 5-year-old kid, you know, who's fucking like a toddler, diapers and shit, how would you explain your solution to me?
I guess I would say something like, hey, these are the 2 nodes that we're looking for, and whichever node is at the very top, we want to return that one because that's the one that has the ones that we're looking for underneath it.
Okay, that's the problem. The solution, there's a very obvious solution here that you could do. What is that solution?
I guess like when we keep iterating or going through this graph, we can keep track of the previous nodes that we've seen.
Okay.
And when we get to a case where we see that these nodes that are given to us is underneath it, then we can just return that previous node.
Okay, give me an example of what you mean by this for like 6 and 8.
Okay, so like let's say when we were going through the 6 and 8.
You write it out. I want you to write it out here.
Okay.
Yeah, go ahead.
So if we're going through 6 and 8, then we could say, okay, if we're visiting the left side, we can say, all right, we're gonna go to 3, we're gonna go to 5, and then we're going to go to 6,
Okay.
and we're going to see that we were able to get to a point where we found one of the elements.
Mm-hmm.
So we know that the lowest common ancestor for this is clearly 3.
Why? Because you haven't found 8 yet.
Oh.
I don't know what
You are right. You are right. You are right. We don't know that. We don't know that. Right now, if so, instead, I'm going to say that we'll also, before we make any answer, we're going to visit the right-hand side. And when we get to a case when we see this 8, then I guess what we could also do is keep track. Oh, that wouldn't really work. I was thinking about levels, but yeah, levels wouldn't really do anything.
Just follow me on this. Just keep going with what you're doing right now. So you found a path from the root to the node, right?
Right.
And so you're saying that we just look for the latest node in these paths that are common.
Right.
Okay. See, that is a solution that you should have came at me with at the very beginning.
Yeah.
See,
No, I 100% agree.
Yeah, you can solve this. Like, it's not hard. Like, literally right now, once I made you solve it in a very, like, brain dead solution, you came up with an answer. So,
Right.
that is an answer. But like I said in the very beginning, it's not necessarily the perfect answer because, let me ask you, what is imperfect about this situation, about this solution? What are the inefficiencies?
I guess like the inefficiencies is storing like those previous nodes.
Sure.
And it's probably possible that we don't clearly have to do that.
Okay. What's another inefficiency?
Let's see. I'm honestly not too sure.
Aren't you traversing the tree twice?
I was just going to say that we're going left first and then we're going right.
Yeah, you're just basically, like, potentially what you could be doing is, like, let's say it was in the case of 6 and 2. You start 3, 5, 6, you find 6, and then you start again, 3, 5, 6, and then 2.
Right.
So, yeah, you're giving up way too easily. It's like, there's a very simple order to this shit. It's like, just start with a brain dead solution, and then you understand the inefficiencies. So, it's like, 1, is that using extra space. 2, traversing multiple times. So, knowing that, and knowing that you have this solution, can you come up with a better solution that eliminates these inefficiencies?
Yeah, so I guess if we were to think about, okay, so I'll first think about like what the inefficient way would look.
No, you already have
like
the inefficient way. This is the inefficient way, and we're saying that this is why it's inefficient. So, can you come up with a solution that first does not use extra space? Let's put that one.
Right. So if it doesn't use extra space, yeah, that's when we'll have to do the DFS with a bunch of different if conditions is what I'm thinking, but I know that's not a good answer to your question because it doesn't solve it at all.
Why is that not a good answer? What is the problem with telling me this?
I'm not giving you a solution.
Yep. You're not giving me a solution. You're just telling me DFS is just a way of traversing a tree. It's not a solution in and of itself, and very rarely is it.
Right.
So,
yeah. So I guess like, okay, let me take another shot at this. So if we were to think about the efficient approach, without using any extra space, then we'll probably have to just, for the sake of time, I'm going to say, or not sake of time, for the sake of explanation, let's say like if we were to write this function, we can keep track of the current route that we're on.
Okay.
And we can also keep track of the 2 nodes that are already given to us. And as we go through the iteration, this current node will basically help us traverse the graph in a way that will help us find if we are able to find those. I keep getting back to how I explain things, and it's just so bad.
Now, I think a very simple solution, very brain dead solution. Don't try to overcomplicate it. How can we? Because the problem right now is that your space grows with how long the path is to get to the node, right? So,
Right.
can we come up with a solution that may not necessarily use extra space, but uses less space than that?
Sure. So I guess like hmm. So you're saying that maybe use less space, but we can still use space? Is that what you're saying? Or do we want to still go around the track
Okay,
where
let me
assuming we
first
have no
start off by
space?
saying, what is the time space complexity of the naive solution that you gave me?
So that one, the time complexity would still be O of n,
Okay,
and the space complexity would be O of n as well.
sure. Now, knowing that, sorry, let me write this. Time order n, space order n. Knowing that, what is your next option for the for the space complexity? Since we're handling that.
Yeah, so then for the next option would obviously, I'm not actually entirely sure if we can get to a constant space.
Okay.
Because obviously if we were to write this recursively, I believe we can still say like the recursion
What did you
stack.
do here?
Okay. So this can be solved with constant space?
Yeah. So, brain dead solution time. Don't worry about recursion. Don't worry about these things. What is what is like another way that you can think about this? Instead of trying to do the path to that node, what's another way that you can do this?
Okay. Instead of using the path, let's think.
What is a constant space version of this?
So I guess what we can do then is when we visit a node, we can visit all the other nodes underneath that given node.
Sure.
And if any of them are equal to the two elements that we are given, then we can return true, or not return true, return the lowest common ancestor. But when explaining that, it's like still hard for me to see how that approach would work for a situation like 6 and 8.
Okay. That is a solution. Yes, that like you did describe me something better. That's for sure. You said that if we can find both nodes in the subtrees underneath it, then we can use those as flags, and that flag would be constant space.
Right.
So, let's massage that idea a little bit more. Can we do something about this flag? For instance, how do I know that my node, using your flag idea, is the lowest common ancestor?
Right. So I guess like at a very like high level idea, if we, for the example of like 6 and 8, if we can see that there's clearly a flag on the left hand side and there's a flag on the right hand side, then we know that the lowest common ancestor then must just be the root.
Sounds like a pretty good idea to me. Does that sound like a good idea to you?
Yeah.
See? Now you came up with something that uses like constant space. Like, okay, all we need to do is just find out if one of the nodes is on the left side or one of the nodes is on the right side. And just flag it.
Right.
Yeah. See, that seems like it would work. Now, of course, you do trade off. What is the trade-off here?
In terms of like what we previously came up with?
Yeah, so let's say that we use your idea of checking every single node and then like checking left side, right side. What is the drawback here?
Let's see. I guess the drawback would be is let. I'm not sure. Like, are we assuming like what if the one of the nodes that we're looking for is like all the way at the bottom?
No. I'm saying what is the inefficiency? Like, because whenever we make a design decision, we don't necessarily get things for free. Usually we pay a penalty in that. What is that penalty? What is the inefficiency that we suffer because of this?
I guess it would be like how we would have to update our flag as we go.
Not necessarily. Well, not necessarily. That's just a coding inefficiency. I'm talking about in terms of an algorithm inefficiency.
So is this still along the lines of traversing each side?
Yeah.
Okay. I'm a little stumped because if we were to use flags to find the left on the left and right hand side, I guess like the only inefficiency that I personally see is that we're kind of just traversing multiple times, possibly.
Yeah. That seems like an inefficiency to me.
Right.
Like, I don't know, does that seem inefficient to you?
Yeah, because it's possible that we're just going to be visiting things that are kind of pointless.
Mm-hmm. Yeah, like for instance, we're just, like for 3, if we're at 3, we'll be looking at like 5, 6, 2, 7, 4, 1, 0, 8, and then we'll be looking at 5, and then 5 will have to traverse down 6, and then 2, 7, 4, etc., etc.
Yeah.
That seems pretty inefficient to me. I don't know about you. Does it seem inefficient to you?
Right, because like you said in the first example, like we literally don't need to visit 274, but we still are going to.
Yeah. So let's write that down. So solution 2, use flags, but then we're still traversing multiple times. Okay, so now that we have this in a pretty good space, I would say space being in constant space is pretty good. What is a way that we can massage this solution into actually removing this multiple traversals?
Removing the multiple traversals. So I guess like one way that we could remove that is by trying to think here. Like, do you mean like just traversing both sides at once?
No, I'm saying that if we're traversing multiple times and we're using an order n or like probably n squared solution really here or
right.
something like that, how can we get this lower? How can we reduce this time complexity?
So clearly to reduce it, we would just have to stop traversing multiple times.
Okay.
So I'm trying to come up with that idea of how we would not have to traverse multiple times.
Okay.
Let's see here. I'm a little stumped. So if we were to use a single traversal without any extra space, then we would clearly, I know this sounds like super simple, but I'm trying to understand in my head. We would clearly have to start like at the root.
Okay.
And we would keep checking if the current route that we're on, if any of the given nodes that we have, which is node 1 and node 2, if it matches the route, then the route itself is the longest common ancestor.
Okay.
And now we can think, well, what if the root isn't equal to any of these, of the two nodes that were given?
Okay.
Then that's when we can simply recurse on like the left and right hand subtrees.
Sure. So keep in mind, recursion is just a function call fundamentally. So what do you expect to get back out of it?
So if we were to, so the call itself will return the current route that we're on. So essentially the next route.
Okay.
For the given subtree that we're
I want
on.
to write that out. So let's say I have my function recurse, right? What am I putting in here? And then what am I returning?
Sure. So if we had a function recurse, then we can say, all right, if we're at the root, we're going to pass in the left, and we're going to pass in the two elements.
Okay.
And this is going to return the next root on the left subtree.
Wait, what do you mean next root? Do you mean the root dot left or node that you passed in?
Right.
Well, I'm gonna challenge you on this. You said you wanted to use flags to find the left and right side, right?
Right.
Do you want to try reusing that idea?
Sure. So, sorry, I thought we moved on from the flag idea.
No, I'm saying that this is good because you give up something, right? So,
yeah.
Is there, because if you just, let's say you found a way to do this in order n space, order to n time, right? Then you're just back to where you started. You know, your base case was order time, order n, but then you got this down to order 1, right? But then what you ended up doing was causing this to go to order n squared, right?
Right.
So if you try to decrease, let me put it this way. Is there a way that you can get this to lower than order n?
No.
Okay. So you already have an pretty optimal way, I would argue, of using space. It's constant. Can we just preserve that?
Yes.
So why don't you try preserving it?
Okay. I'm a little stumped on how come you placed just node here?
Because this could be any node, right?
Okay, so you're just saying, like, who cares about the left or right subtree? What is this actually returning is what you're asking.
Yeah, because basically what I'm throwing into a recursion is really just a node, any node, right?
Right.
And from once I'm inside the function call, I don't know if this came from a left tree or a right tree. You know, I don't know. All I know is just it's a node, right?
Mm-hmm.
So, the question here is like, okay, well, now that I passed in all this information, as with any function call, what do I expect to get out of it? What am I doing here? What do I expect to get out?
So we would expect to get out, I'm a bit confused. I mean, wouldn't it just be the current route that we're on?
No. When let's say I have some function like foo, like that just like adds numbers, you know, and I add an int. I'm gonna get back, you know, an int, right?
Right.
So I'm asking you, this int represents me adding two integers together or some shit like that. I'm asking you, what is the equivalent here? Because again, recursion is just fundamentally a function call. What am I getting out of this?
Literally just a node.
Why would I be getting a node?
Because that's what our function's returning.
No, that's because you wanted to return that.
Great.
So my question to you is, why are you returning the node? Why do you want it to return a node to begin with?
So that we can keep track of where we currently are in the tree.
That does not make sense. You already know where you are in the tree. Like, let me give you an example. I think you don't understand recursion. So let me give you a little tip. So let's say I call this function. Let's say I'm at node 5, right? Node 5. Right. And so I make this call recurse, right? to my left subtree, 6, and then my n1, let's say it's 7, 4 for argument's sake, right?
Mhm.
So now I'm in node 6, right?
Right.
And all I do is like some shit, right? And I come back out. I'm still in node 5 when I pop back out of the recursion. Why do I need to return node 6?
Right. So we don't.
Yeah, so I don't understand where this is coming from. I don't understand why you say we have to return a node because that's just the way it is. You can return whatever the hell you want.
Right.
Like, you can return null for all I care, you know? You can just visit the nodes and do nothing. So, my question to you, again, is what do you expect this recursion to actually give you?
The longest common ancestor.
Wait, why? Like, you have these flags, right? You're using these flags to figure out the longest common ancestor, right?
Right.
So, how exactly can you use these flags to help you? Where does this come in?
So I guess, I mean, they come in to help us to basically know, obviously, where these elements are. But so then when we return, we're just returning yeah, I gotta say I'm a little confused.
Okay, you know what? Maybe I give you the answer and you'll understand. Why not just return whether or not you found one of the nodes? Your flags. Can you
Right.
return a flag?
Sure.
Are you confused now still, or less confused, or?
So what exactly do you mean, like, can we just return the flag?
So you said that if we find the nodes in the left subtree and the right subtree, that we will have found our lowest common ancestor, right?
Right.
So this recursion could just represent, hey, in the left subtree rooted at 5, I found, let's say, n1. Can we just return that information?
I guess we can.
Why can't we? You say yes. What's preventing you from doing that?
I'm just still, I guess I'm not convinced that at that point we really know what the lowest common ancestor is.
Okay, but like you said, if you can find the node, it doesn't have to be like you said. Let me rewind. Let me make it a little bit clearer for you. So, like you said, if we find one of the nodes in the left subtree and one of the nodes in the right subtree, we have found our lowest common ancestor.
Right.
So, can I use recurse to say, hey, given the root of this tree and the nodes I'm looking for, can I return whether or not that I have found that node or one of the nodes, right?
Right.
So, I can just call recurse on the node left subtree and the node right. Does that
Okay.
work?
Yeah.
Are you confused still?
It makes a little bit more sense.
All I'm doing is just running with your idea of use flags to find left and right. And based on what you said to me, if we find these nodes in the left subtree and the right subtree, then we have found our lowest common ancestor. This is literally what you just told me.
Right.
So, can I use recursion, this function call, to magically do it for me?
Yes.
So, it's like you already have it up there. Right? It's like just draw the fucking line to your fucking idea.
Right.
Like,
Yeah.
so it's like I'm really trying to understand like where this confusion is coming from, and I think I know where it is now. It's like if the answer is not immediately obvious to you, you don't try to do anything. You're just like, oh, I don't know. But I'm like, you kind of have the pieces here. I'm really just like pushing you, like, hey, you literally have this idea right here. Just return whether or not you found it in the left subtree and the right subtree.
Yeah. And that's like exactly what I mean of like what I found is my problem. Is like I can come up with not solutions, like, but like solid ideas. And then when I tried to like actually really, really like put it together, if I can't get it like immediately, I just give up.
it's like it's not even that you come up with the idea. It's not you don't really have the idea. It's like I said, there's an efficiency to this. There's a way of building upon your previous idea. So I think one of the things that we can quickly like do a tangent on is really just like your understanding of recursion. I think that's going to help some people in the chat too. And so let's quickly redo this, and I'll give you a visual example of this. So let's actually look at this. Is this? So hold up. Let me share my screen with you for a second.
Okay.
Can you see this? Oh wait, other one. Oops. Let me go ahead and change the screens. All right, can you see this? My iPad.
I think it's loading.
Let me
now.
know. You see it now, right?
Yep.
Okay, so let's say that I have any number of like this is a random tree, right? I don't give a shit what these nodes are. You know. So essentially, what all I'm doing with a recursive call is just saying, hey, I'm segmenting this off. I don't know what the fuck's happening down here. It could be like a bunch of nodes. It could be one node. It could be whatever the fuck I want, right? And all I'm really doing is plugging in some values. And then there's a terrible fucking color. Hold up. So all I'm doing here is as I'm plugging in some values, fundamentally, because it's a function call, right? And then I expect to get back some, let's say get blue. I'm getting back some output, right? This output could represent something, but I'm doing some kind of processing on this, like fucking think of like an ice cream machine, you know? I'm turning the fucking cream, water, and whatever disgusting shit into ice cream. That's essentially what's happening here.
Right.
So, but in this case, in our world, what we're really plugging in is really just this node here. We're saying, hey, I'm plugging you a node, my node.left, and then I'm plugging in some value 1 value 2, or whatever, right? And then my output will just be some object or value that represents something. I don't know what that something is, but in this particular case, this something just means, hey, whether or not I have found the value 1 or value 2 in the subtree.
Right.
So if I'm in here and calling the function, I'm just looking at this and say, hey, magic fucking ice cream machine, tell me if one of these values exists in your subtree. That's it. That's all recursion really is. It just means it's just a function that just happens to call itself.
Right.
So that's what you can, like, when you go ahead and write recursion, you can think of replacing it, instead of calling it recursion, you can call it like black box or something. And then in here, you say, hey, this black box will guarantee me some result. Like, it could be some external magic function that some senior developer has written that will do exactly what you said.
Yeah.
And then eventually what you get to a point where you can actually call, instead of replace this with recursion, and it'll do exactly the same thing.
Yeah.
So that's essentially what all recursion is. It's just a function that calls itself, but fundamentally, it's still just a function that we put in something, we get some shit out. So
yeah,
let's take your exact what you exactly said before. So you said that we're gonna plug in so that we're gonna just look at a node. This node could be attached to whatever the fuck in top, right? So the first thing we're gonna do is just check to see node, right? We're gonna just say look at node, and then look at left, right? And then we're gonna get back whether or not this has one of the the targets, N1 or N2, and then we do the same thing on the right side. Whether or not has one of the targets. And then if both flags are true, then return, then we found our solution. Right?
Right.
Now, this is a very, very basic way of doing things. Now, like you said, this is in this recursion case, we now have set ourselves up for recursion because, hey, this is going to tell us that we need to return back whether or not we have one of the targets by definition of what we just said. So, in other words, this function call here needs to tell us whether or not we have found the targets in the left subtree or the right subtree, right? Whether or not we found them.
Right.
And technically, this is true. But it's also true that we found both of them. So the next step now becomes, how do I reflect this? That realistically, I know that this is correct, you know? So how do I save this as my solution? This is the part you're getting at. And so this is where I think you also got stuck.
Yeah, this is honestly where I was like the most confused.
It's like, okay, well, we have a basic template. We know that it works. We just need to go on to the next step, you know? Like I said, there's an order to this, step by step, chunk by chunk, you know? Baby steps. You don't solve the problem right off the bat. You always solve it with piece by piece and optimization on top of optimization. And you saw that all we did here was take some very obvious facts that you yourself gave me, and we just added them to the pile.
Right.
That's it. And so now that you understand where this is coming from, do you think you can continue with the problem? Because I get the feeling you're getting very frustrated.
Yeah, this is very frustrating.
Right.
But and part of the process.
It's part of the process, but like I said, it's fucking baby steps. Now, it's just because there is one little hiccup in the solution. It's just like, okay, well, is it better than what we had before? Yes. Then all we have to do is just figure this one part out, and then we move on, right?
Right.
So, yeah, you can see we're already starting to build up the solution that we want. So now the question becomes, okay, let's say I did find a solution. I did find the lowest common ancestor in the tree. You know, there might be some shit up here. I don't know. You know? So the question now is, how do you want to save the solution?
Right. So I guess the way we save the solution is I don't know, I guess we can have two trackers that are going to be doing the recursion on both sides.
Okay.
And so obviously we know that we'll have we can say a variable, something that keeps track of the right side elements, the right routes that we visit.
Okay.
And we also know that we'll also keep a variable, we'll say, that keeps track of eventually all of the nodes that we visit on the right side and for the left side.
Okay.
And so we can use those to basically tell us what the lowest common ancestor is. Because
don't overcomplicate it. There's a very simple way of doing this. Very simple, brain dead, you're overthinking this.
Okay, then we know that at the end we're either going to return left or right.
No, you just said if it has one of the targets. So fundamentally, this must be a Boolean.
Okay, so you're saying... Oh, okay, so then you're basically saying all right, so are we assuming that left and right are the flags in a way?
Right. We defined earlier. We're
Okay.
we're putting in some values, and we're getting back whether or not that we found. Oops.
Okay, then we return whatever flag is flagged for true.
Okay, so you want to return true. Okay, but then, what is the problem with this?
The problem with that is, I'm not sure. So are you saying maybe, because the way that I'm thinking now, that it's possible that both of the flags are set to true? Is that kind of what you're getting at?
Well, let me make this clear. So let's say that we return true, that in the case that we have found our solution, and that we're mixing up a bunch of signals. So let me make it clear. So let's say we're looking for this node and this node, right?
Yeah.
So, I go ahead. I'm gonna use this color. Let's say I'm in this node right now. I traversed to my tree. I found this node, right?
Oh, your screen share just disconnected for me.
Okay, hold up. Let me try again.
Okay.
Do you see it now?
Yep, I can see now.
Great. So let's say the purple is what I'm looking is my target nodes, right?
Right.
And let's say my red is the node I'm currently looking at, right?
Right.
We call our recurse function. Boom. We plug in this node, and we get back true. Right?
Right.
Because I found one of them. We do this again here. Boom. I return back true. Right?
Right.
So then now I recurse back up. Let's use a change of color. I recurse back up and return true like you said. Now I'm in this node, right? And I see true. Well, does that mean it's true because I found one of the nodes? Or
No.
is it true because I found both the nodes? Or is it true because I found my actual answer to the entire solution? I don't know. You
Right.
overloaded this flag with all that information. Now, this is the problem I'm talking about. So then I go to here and I say false, right?
Right.
Because it's not one of the nodes. And so here, I return back what?
So it would be false.
Okay, it's false. So then, did we just lose our lowest common ancestor solution?
We did not,
Why?
because we're only staying true to where the lowest common ancestor actually is.
Okay,
And
fine.
we're
Fine. So fine. So then, let's say I'm finished all my entire function. How do I return back to the program this node?
um let's see. Hmm.
I'm telling you, there's a very simple way of doing this.
Is it Hmm. Are we implying it's something along the lines that we know that it's either going to exist on the left or the right side?
No, I'm saying when I need to go to the program and say, hey, I need to return to a node, right?
Right.
How am I going to do that?
I guess like at the very high level, we would only return the one that has the flag true on it, but I know that's not what you're looking for.
Something very, very easy, because, there's so many nodes here that return true.
Right. Um, yeah, I'm a bit stumped.
How about having a global flag?
Okay.
Node
Sure.
answer.
So then I guess if we were to have a global flag, we would only update that flag when we hit a true case.
Yeah.
And
Once I found my solution, boom, I got my answer. Now I have something to return back to the program.
right.
Was that simple, or was that not simple?
It was simple. Just me doing me, overthinking.
Yeah. Again, like I said, this is the lesson here today. It's like, if you can get in your head that these answers are built from very, very simple observations and optimizations, you will basically be halfway there.
Yeah.
At least with regards to practicing. So, let's go back to this. So, knowing that we now are going to set our global flag, that we found our solution, set our global flag. Now, now we have these checks here. Like you said before, we need to be able to do our what's it called? Our checks on the node. So, these are quote unquote our base cases. How do we want to handle
Right.
these?
So we could clearly do the obvious and check if we hit a null node. And in that case, we So if we're doing obviously the recursion, then we would just return the root so that we can keep going.
Okay, so our base case is
then-
going to be null. What else?
If the current element that we're looking at, if it's equal to one of the node 1 or node 2, whatever we want to call it, then yeah, that's another base case that we can run into,
Okay, that's
which
fine.
we would return or update our flag.
Mm-hmm. Yeah, so you just return true.
Yeah.
Okay, that's fine, because you found one of the targets, right? Like, that was the whole point of the function. Did you find one of the targets?
Right.
So, we're going to stop the problem here. But overall, you see, like, we're basically pretty close to a solution. There are a few edge cases that need to be handled, but you can see at least we have something that works.
Yeah.
So, I want to know your thoughts right now, how you're feeling, how you felt about this exercise, and all that jazz.
I think this was good because, like, in an interview, obviously it's not the same as this where you can the interviewer is helping you draw up stuff you didn't see. But I think this made it very clear on how, like, I've been approaching things. Because, like, if it's a problem that I've seen before and I'm comfortable with, obviously, like anyone, I would suppose, can explain it very well and be confident about it. But when I get stumped like this, as we saw today, like, I will freeze up if, like, my solution isn't incredibly clear to me at first, instead of, like, doing what you said, where, you know, you're basically giving yourself really good stuff, but you're doing nothing with it.
Yeah. All it is just building this piece step by step. I'm going to tell you that anyone doing this particular problem, this is like a LeetCode medium or easy-ish problem. I'm going to tell you that anyone who is even remotely comfortable with trees could solve this problem in 15 minutes. Like, the whole process that we described would literally just happen within 5 minutes instead of it taking a full hour.
Yeah, I 100% agree.
So basically, if you can get this down right, the basics, then you can just do this faster and faster and faster. But this is the fundamental basic out of everything or any problem that you will be doing. You need to be able to do at least this.
Yeah, no, I 100% agree.
Okay, so I'm gonna leave it here. You can look this problem up yourself. I'm gonna go to another problem. But what I want you to really do in this next problem is really apply what we've talked about. Just start off slow, simple, dead-ass brain case. Notice here that I didn't even talk about, like, any crazy-ass topic, any computer science, like recursion or anything like that. It just kind of happened naturally, you know? I want you to try adopt this. Take things piece by piece, step by step. Come up with a simple solution first. Understand what is wrong with it, why it's not necessarily optimal, and then try to improve on that. And then see if you can carry that forward. You know, sometimes you can't, you know? But at least try it.
Okay.
So, let me stop sharing my screen and I'll give you another problem.
Okay.
I want to give you something along the same vein, actually. Oh, this one should be easy. Oh wait, no, that one's a little too easy. Hold up. No, not this one. Okay, oh yeah, so this one. So, given a root of a binary tree, I want you to determine if it is a valid binary search tree. So, what do I mean by this? A valid binary search tree is going to be defined as the following. The left subtree of a node contains only nodes with keys less than the node's key, and then the right subtree contains nodes only greater with the node's right key, right? And then both the left subtree and right subtree must also be binary search trees. So, think you can do this?
Yeah, I can give a shot at this one.
Cool. Remember, and I want you to really focus on this. Simple, slow steps, simple optimizations. No magic bullets. I want you to keep this in mind.
Okay. Yeah. No, I agree. So yeah. So for this, yeah, if we were to just review of what a binary search tree is, so, the left subtree obviously can only have nodes that are less than it, and the right subtree can only contain nodes that are greater. So maybe you think I can actually grab the graph or tree from up top and kind of do an example on that one?
Sorry, you're saying you want a solid example of this?
Yeah, I was wondering if we could reuse the picture of that tree up top.
Sure, but this is not a valid binary search tree.
Right, which is true.
I mean, yeah. So I mean, what kind of example are you really looking for?
Yeah, you're right. There's actually really no reason to do that.
I mean,
So
I could, but it's like.
no, you're right. I can do it without it. So if we wanted to do, slow steps, simple optimizations, so we can clearly start at the given root. And every time we're at a given root, we want to clearly check its two neighbors that we have, which is our left-hand side and our right-hand side.
Okay.
And we want to see if these obviously follow this structure up here where the left subtree is less than the current node we're at, and if the right subtree is greater. So if we were to do that, it would kind of be like the very simple approach, right? It's basically saying like, let's keep on going through this tree, and let's keep checking if at each root that we're at, if its left side and right side follow these conditions. But the issue with this is obviously keeping track of the values as we traverse the tree. And by values, I mean like probably some type of maximum and some type of minimum to help us keep track of, we could say these nodes with the keys less than and the keys that are greater.
Okay.
So if we wanted to do, again, trying to keep it simple here without explaining like the code or anything, we can probably keep track of maybe like a global global variable that will keep track of
I
the
think
last.
you're jumping in way too. You're making too many jumps here. I want you to actually start writing out your idea. Give me the pseudocode for it.
Okay. So the pseudocode would be something along the
And remember,
lines
keep
of.
this pseudocode like brain dead, like as if you are describing this to a fucking 5-year-old child.
Okay, so let's say we have something that tells us if it's valid. And we'll use this as some type of flag to basically call some other black box function that we'll pass in our tree to.
Okay.
So maybe that'll look like.
I think you're getting into code right now, but I want you to describe the algorithm to me.
Okay, so
again,
I'm trying to.
Again, I'm fucking 5 years old.
Okay, we want to visit each root, and this valid flag is going to tell us whether or not if it follows these conditions. The left being less and the right being greater. And what we're going to eventually do is return this valid to tell us whether or not our binary tree is a valid binary search tree. So now can I kind of go a bit more into what this might look like?
Sure.
Okay. So I would say it's safe to say that we're probably going to pass, as given in the description, the root of
Okay.
this tree. And I would also say it's safe to say that, as I mentioned before, we're going to keep track of some type of minimum and some type of maximum that will help us keep track of the left and right keys.
Mhm.
So this black box, without going into code, I'm just going to explain what we would ideally want it to do.
Mhm.
So we would want this to basically update our value
Okay.
on the left, update our value, and I'll specify the values. I'm
Okay.
just writing a bit out a little here.
Okay, sure. You're just doing like a brain dump or whatever. Sure.
Yeah. So we know we want to update the values on the left. We know we want to update the values on the right. And we also, within this black box, we want to return when we break I'll call it like the main case.
Okay.
And the main case will be basically these descriptors up here.
Sure.
So now I'll go to how we will update these values.
Okay.
So when we are updating the value on the left, we're going to want to update our maximum value.
Okay.
So, and we would keep the minimum value the same.
Okay.
So for this, we can say that the call might look something like, hey, keep this maximum the same,
Okay.
but for the minimum, let's pass in the value that's on the left
Hold
of
up.
this.
Why? You just said that you're updating your max value. Why are you passing in to minimum?
Yes, you are right. I'm sorry.
That's why I had
So-
you write it out.
Yep. Thank you. So then it would be root.val.
Okay, sure.
And then for this one, it would basically be the same idea, but I mislabeled this. So
Sure.
we are calling it on the left, but yes, we are updating the maximum, not the minimum. So then if we take this, we're going to change this to the right, and we'll change this back to our max because we're updating our minimum here. And our minimum will be updated to the value of our current root,
Okay.
keeping the maximum the same.
Sure.
But it's worth noting when we can update these, right?
Okay.
So I will cover that now. So I'll try to indent these a bit so we can think about this as like sub-steps to
Sure.
only if this is true.
Mm-hmm.
So we know that we can only update some values when our given root is either less than the value or not the value. If the given root's value is less than the maximum,
Okay.
and if the given root's value is greater than our minimum,
Okay.
then that is the only time that we can update our values.
Okay. That's your valid case. Fine.
Right.
So I want you to write that down.
Okay, so I'll say if the current root val is greater than our min, and if it is less than our max, then we can update.
Okay.
Okay, so that's okay, so I'm gonna delete this for now.
Okay.
So this is the case to when we can update.
Mhm.
But now we can think about the other case that is kind of outside of this.
Okay.
So if we do this, we know that we're gonna essentially, if we say this is, the black box function, we're gonna recursively call this. And this is where they're being recursively called.
Mm-hmm.
And if this isn't the case, then we can probably just return false.
Okay.
Because we know we basically hit the case where it's not valid.
Okay.
So I think that's how the black box valid or function would work.
Okay.
And then this valid flag will pretty much be not trying to get into code, but
Sure.
a Boolean value.
That's fine. You're declaring what exactly you expect out of the function. I have no problem with that.
Sure. So then the way that this recursion is working is essentially saying that we will know that whatever this valid ends up being, we can simply return it.
Sure. Now, are there any other because right now you've only specified you're returning false. Are there any other cases you want to return maybe true for?
Sure. So we can always, in this black box, before we actually even do this, we should check the simplest case, right? Where if the root that we're at is null, then we know that we can return true. And that would technically be the only time that we would return true.
Are you sure that's the only time you return true? Because what you just told me is that we only return true if the tree is null and false every other time. Does that strike you as a problem?
Yeah. Right. So okay, so here we're clearly going to recursively call this, and then otherwise we're gonna return false. So we'll probably, I think if we write this as a helper method and kind of have this valid in the main method, that this would still work if we have that case of if the root is equal to null, then we just return true.
Okay, but what I'm saying is that let's say you did all this update. Do you still want to return false? Not to mention, what happens if this black box returns false or true?
But here we're technically returning when we do.
You didn't tell me that because, well, what do you?
Okay.
You didn't tell me that. I don't know that. That's what I've been asking you.
Okay.
If it's not written down, I don't know it exists, and you didn't tell me either. So.
Okay. Yeah. No, you're 100% right. So, essentially, we are returning both of these in a way.
Okay.
And so I guess I'll just do this down here and say we're technically returning both calls, and these calls are updating our I'll just say min and max. So again, these are updating and returning.
Okay, so when you return both these calls, you have a Boolean coming from the left side, a Boolean coming from the right side. What is the relationship between the two?
Right, so it's essentially only going to return when both of them are true.
Okay, so if both of them are true, you're going to return a...
So right now, what would be returned would just be true.
Okay, so like I said, if both of them return true, what are you going to return?
True.
Okay, if one of them is false, what are you going to return?
False.
And if both of them are false, what are you going to return?
False.
Okay, so you saying return both these calls makes 0 sense.
Right.
Like I don't know
should
why
specify that.
you use words like obviously, clearly, but your writing and the way you explain things aren't very obvious or clear.
Yeah, I agree.
So instead of being very vague like this, be a little bit more atomic and a little bit more detailed. So what are you gonna write here instead of writing returning both calls?
Instead of, yeah, so then here we should say it returned, or instead of saying returning both calls, not just here, we can say something like returning true or false based on what both functions return.
How's that any different? Why not just tell me the relationship?
By relationship, like whenever they're both true and both false.
Yeah. What's the relationship?
Okay, so when we get true, then we are updating both our max and min and returning true. And when we get true false, we are returning false. But we are also updating the values. And then when we get false, we're still updating the values, but we're returning false.
Okay. And so what logical operation is this?
So this is an and.
Yeah, so why not just say
Operation.
and? Yeah, instead of making it
Okay.
so complicated, just say and. And second, this updating value, like, what do you mean updating value?
By updating the value, I mean that we're basically updating whatever is going to be in place of this min and max.
So if let's say I went through 5, 6, 2, blah, 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 whatever. Let's say, when I pop out of 5, am I going to remember these changes?
So you're saying like when you leave 5 and you go to 6 and 2?
Let's say I'm doing a depth first search, like you said. You're traversing left, traversing right, right? I'm at 3.
Mhm.
I go into 5. I come out of 5. What are my maximum and minimums for 1?
So at that point, your left maximum, well, for left, your minimum would be, so I guess that poses the question of what we would first assign them to. So I guess we can assign them to like infinity and negative infinity.
Okay, sure. But let's say you ran. Let me draw you an example, and I want you to tell me exactly what your algorithm is going to return. Give me a second.
Okay.
Okay, let me share my screen again. So suppose I gave you, like, say, 5, and then 2, and then there's a 7, and then...
Discord.
Okay, it's still running. Let me know when you see it.
It's you're sharing Discord.
Again. Got it?
Yes.
So let's say I have this very simple example, like, and then I'm at 5, right? What am I passing into 2, and what am I getting out?
So once you're at 5 and you're going to 2, you are returning that so let's see. So yeah, you're updating the maximum. So it would be 2.
Okay, so let's say I like you said, we have a function call where we have a node, min, max, right?
Right.
So when I go into here, the node's going to be 2, but then what's my min and max going to be?
So your min will be 2 and your max will be 5.
When I go in here?
So because when we're calling just on the left subtree, it's only updating the maximum value.
Okay.
So we could say that it could be like 2, 0 or whatever we want to place there for now.
I would say negative
And-
infinity. Let's just say negative
Yeah,
infinity.
negative infinity,
Okay, fine.
and
Okay.
then it would be 5.
Fine. So then now I'm going to recurse in my left subtree per your algorithm. What am I passing in here?
So now it would be 1, still negative infinity, and it would, let's see, so now we would compare 5 with 2, and we would leave 5.
You want 5 to be our maximum.
Or I'm sorry, it would be updated to 1.
You want 1 to be your maximum.
Right. So, well, the current root we're at is 1.
No, we're at 2.
And-
We're at 2. We're going a function called a 1.
Oh, we're at 2. Okay, so then 2 is not greater, or it's less than our max. So, yeah, our max will be updated to then 2 right now.
Okay, fine. All right, and then we pop back out, and then we say whether or not it's true. We're at 1. We're passing in, like you said, 1. We're passing in null because this is a null, negative infinity, and then you're gonna pass, and then you pass in what's it 1 per your own argument, right?
Yes.
Okay, pop back out, and you say it's valid, true. Okay, we go into here. What's the values that we're working with here?
So now we will pass 3,
Okay.
and this will obviously be for our right case.
Okay.
And the value right now, we would pass. So it would have probably first
What's
be
my minimum? What's my max?
okay. So right now we would just pass in 3.
3 is your minimum? What's my minimum? What's my maximum?
Or right now your minimum is negative infinity.
Okay.
So our maximum would just be 3.
Really? Like this? On the right hand side?
Oh, not on the right hand side. I'm
Like I
sorry.
said, we're on the 3. We're trying to get in here.
Right.
Keep in mind.
Yes. So if we're on the right side, then we're updating obviously our minimum.
Okay. So what are we updating it
So-
to?
So our minimum right now would be still negative. No, it would become 3.
So we're gonna go into 3 and pass in 3 as the minimum.
No, that doesn't make sense. So yeah, it would still be negative infinity then,
We want to make negative infinity our minimum.
right?
Why?
Because that's clearly smaller than 3.
No, we're going into 3. What if this was negative? What if this was negative 10?
Well, oh, like why are we making it negative infinity?
Yeah. Why?
Well, that's because, like you said here, it's possible that we deal with negative numbers,
Okay.
and we want to have a value that's incredibly small.
Okay. So then, what's the maximum value we're gonna pass in?
Then the maximum would just be negative 10.
Why? So you could say negative 10 here, negative 10? Why when you pass into here?
So then our maximum here would be 3, I'm sorry,
What?
right?
I don't understand. Okay. Let's rewind because you're confusing me. So let's say I have a value node of 3, right? You're
Right.
gonna update the minimum to be negative infinity. Is this what you're saying?
Right.
And the maximum is going to be what's the
It's
maximum?
just the current value that we're on.
3.
Right.
Okay, so then let's say I change this value to be negative 10. Would it still be negative infinity, negative 10?
Um, yes.
So you would still say this is a valid binary tree.
Yeah, no, I see what you're saying. Because it's not.
It's not. So what do you want to do? So obviously this isn't the right answer. What do you need to do?
Um, so here, when I'm trying to think, I don't have the document up. I'm trying to think of what I wrote for the right. Um, I believe it said that we pass whatever's at the right, so we have the 3, and then we pass, um, but we only pass when that value that we're at is greater than the minimum and less than the max. So
So
3
how
is
can you would basically have to check that node before you check that node.
right.
Does that make sense?
Yeah.
It actually makes sense to you? That you're checking 3 to be valid before you pass in the value?
No. Yeah, I'm.
All right,
I don't know.
I can tell you you don't know what you're doing. Let me make this easy for you. I'm gonna tell you that you need to update the minimum, and that this maximum just is 5. Do you understand why?
Yeah, because we're just kind of. I guess you'll be able to explain it better than I, but
No, I
it,
need you to explain it because that way I know you understand it. Because right
it's
now when you told me that, you're basically telling me that you don't understand it.
right. It's because we're basically using the minimum and maximums kind of as very like global variables that are going to be updating as we traverse the tree.
That you didn't understand it. No, that's not. You are being way too vague. It's okay to say you don't understand, man.
Yeah, no, I don't get it.
Yeah.
I'm
Okay.
Tree problems are probably my weakest right now.
Okay. So the reason why we do this is because by definition, everything to the right of a tree node must be greater than this node. That's by definition of validity. So the minimum we can ever be is 2.
Right.
This must mean it's like 3, 4, 5, 6, 7. It's still fine, but we have this root here that's preventing us from being any greater than that, because otherwise we would violate this constraint of everything on the left side of this node has to be smaller. So we can't just up and say this is 6 or 7, right?
Right.
That's why 5 must be our maximum. You had some intuition here when we went down the right hand side where you knew you had to update the maximum, but I get the feeling it's because you didn't understand why.
Yeah, you're 100% right.
You just assumed it randomly worked. That's the problem. It's like I said, it all has to boil down to fully understanding what the heck you're given with to begin with. So, doing that, it's like once you understand that, hey, the limitations of let me explain it a different way. Let's say that I had started off the problem myself, and maybe you can copy this as well. Maybe this will make some sense to you. So let's say I start off with the very same problem, right? I'm going to say, hey, everything to the left of this must be less than. Must be less than this. Everything right must be greater. So, which means my minimum when I traverse down this tree my maximum at any point must be 5. Anytime I go to the right, I update maximum to be 5. Anytime I go to the left, the minimum must be 5. Because that way, that will establish my boundaries.
Right.
And so here, let's say I'm at 2, right? I go down to the left-hand side. Okay, following this rule again, everything to the left must be minus, everything to the right must be bigger. The maximum here must be 2. The minimum here must be 2. But I carry over this idea here that everything, because of this root limitation, that the maximum must be 5.
Right.
You see how easy I was able to explain that just based on the rules of the binary tree?
Yeah. No, you're 100% right.
Yeah. This is what I mean. Like, you were just kind of like throwing darts randomly and just kind of hoping an answer falls out. Almost always,
Yeah.
every single time, a problem is going to be built off of these simple facts. And I think that's what you've missed here. You just kind of assumed that you would be able to YOLO the problem.
Yeah.
So, that being said, let's look at what your solution is. That's why I don't think that update is the right way of doing it. You didn't know what you were doing here. So, like, that's why I kept trying to be very specific. Like, what do you mean by returning both calls? What do you mean by doing this? And then when you say update our min, update our max, okay, I'm cool with this. Like, you even wrote here, update our min. You even wrote this here, man. But you didn't understand why you're doing it? Is it because you remembered the problem or something like that?
Probably. I've done it a long time ago. I
Right.
probably remembered like the slight trick to it, but yeah, at the end I didn't quite understand. Like you said, that drawing you did in like 1 minute explains it.
Yeah, exactly. Just even understanding this problem is just going to be just that. You just need to understand how to draw it out and the limitations of the problem. And literally all the limitations of the problem are given to you. So this is why I didn't understand the updating our min and max during this. Like, I don't understand where this is coming from, and you didn't understand where this is coming from. So, you know, and so that's why it led to a lot of discussion and confusion here. So that's the problem, basically. Your problem boils down to you are not able to do this step to begin with. This, what's it called? This, this diagram. Like, being able to illustrate whatever the hell we're doing. Illustrating the core idea. This is why I keep saying, design your problem. Draw it out. Like, describe to me in pseudocode everything you're fucking doing. Being able to grasp this idea here. If you can do this, you will have solved 80 to 90% of your issues.
Yeah,
So,
I agree.
all right. Let me know what you're thinking right now, how you're feeling, if any of this is clicking with you.
No, yeah, this is definitely clicking, and I mean, if anything, today just proved to me of like everything I knew was like wrong with my approach on studying, and like really making sure I understand stuff is like has not been the best approach.
Okay.
And I will say like trees have always been my like hardest subject because of like the whole recursion. But I think if I were to spend some time on trees, I'd be able to solve these much quicker.
Okay. All right. Yeah. So being able to not just understand trees, but being able to draw this out, whether it's for arrays, trees, heaps, I don't give a shit. This right here, being able to explain in very simple terms to anyone what you're doing is absolutely critical to doing these problems correctly. And so this is like your first step. And if I'm going to give you homework, I'm going to say just these very basic things. Draw out the goddamn problem, come up with a very basic idea, and that is very naive. I don't care if you hit the optimal solution. All I care about is you come up with a solution. Because then you can do the exercise that we talked about, which is, oh, what are the inefficiencies in this solution? And how can I get that better? How can I incorporate that? How can I attack these and remove that inefficiency?
Right.
But at least you have a point to start off with. You know, there's once you have a problem and once you have a solution to it, you at least have something that works, and there's something in there that you can take advantage of.
Mm-hmm.
So, with that last 15 minutes, let's talk about like studying for the next few weeks, because you need a lot of work, man. I'm not gonna lie.
Okay.
So let's So give me a second here. Let me pull up some copies. Okay. So let's look. I'm gonna. Hopefully my screen is still sharing.
Let me double check. I went back to the doc.
Okay.
Yeah, it's still sharing.
Okay, great, perfect. So I'm showing you the practice interview diary, right?
Actually, you might have to share and then, or stop sharing and then share again.
Okay. Let me stop share. Okay. So can you see this?
Yes.
I'm gonna make you do this. Literally, like, you see how fucking verbose this is? This is actually one of my clients, man. So he, like, records the date he did a problem, the time, how long it took for him to do the problem, how difficult it was, what problem it was, what topics were covered, and what he did wrong, and what he did right. You know, for instance, shit, this one's is easy. It's such an easy hard. No need for dynamic programming. No need for DFS, post order traversal, so on and so forth. There are 3 possible states. Da 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 da. You get the idea. Basically, he's reflecting on every single problem that he does.
Yeah.
And thinking about how can I do it better? What went right? What went wrong? And this is what I want you to do. I want you from here on out, I want you to be able to keep a diary like this. For any given problem that you do, I want you to be able to fill this out and say, hey, how can I have done this problem better? Why did I get to the solution that they did? What are the steps I need to do in order to go from my current state to the optimal state, you know, to the optimal solution? What were the simple steps that I had to follow? Like the stuff that we did today, you need to be able to record. Like the steps that I did in order to go from a naive to optimal solution, you should write that shit out if that is something that you cannot do. Like if I had thought of this step, if I had this insight, then I can go here. If I had this insight, then I can make this next step. Does that make sense?
Yeah, makes sense.
So I want you to do this for every single problem that you fucking do from here on out. I think I sent you a copy of this practice sheet, and I think that you should make a copy of it and do it. I would recommend you do a few problems and get into the habit of doing this. Now, let's actually talk about your study schedule, because I get that. Let's talk about like how much you study per day and so on and so forth. So let's make a copy of this. So, how many weeks out to the interview do we have for you?
So I don't have a strict date yet, but it will be the earliest, the 11th.
Because what I saw today, you basically are looking at 6 weeks minimum. How good is your pattern recognition? Like if I asked you to write out the pseudocode for a sliding window, how quickly could you do it?
Sliding window pretty dang quick.
All right, you know what? I want you to do it for me right now.
Okay.
Show me the template.
On the same doc?
Same doc, where I've highlighted. I want you to do it. Go, go, go.
Okay. So you always have 2 pointers. So I'll say I, J. They both start at the same position. You have a condition, or here, I'll say even more specific. You have a right pointer, left pointer. You always go up until R goes to the end of whatever you're traversing. You look at the right element, whatever it is. I'll just say X. Move this right pointer. And then you have a condition to where you close the window. And then you have, obviously, where you open the window. And then you usually calculate the size of, like, the window, which is something along the lines of this.
Okay.
And usually this condition in here is like another while loop to whatever. And here's where you actually close the window.
Mm-hmm.
So L++. And you do this up until this condition is broken. And as you do that, depending on the problem, you're obviously updating the size of the window.
Okay, fine. You get the idea here. I personally don't agree with doing an increment because, you know, your answer might be when R is equal to 0 and L is equal to 0. But I think you got the basic idea. Did you plug this? Did you do this while doing grokking?
Yes.
Okay. I mean, I would say be aware of when R and L is equal to 0. That may be a valid condition.
Yeah. And I guess you can simplify that with just making this a for loop that goes over R.
Yeah, it's fine. Okay, so you seem to have a good idea on practice of that. Fine. I'm very wary of this and blending lines like this, but it's fine. All right. So next thing. So I want you to be able to kind of, how to say, I think right now the best thing for you would probably be LeetCode actually. I hate saying that because I fucking hate LeetCode, but yeah. So we're gonna do some LeetCode problems. I want you to start focusing on like just trees for the next couple of days. So let's plan for like 6 weeks minimum. So let's say that you have let's say the week of the 23rd to, let's do it by Thursdays, our streaming, our coaching sessions, 7:22 to 7:28. Okay, 7:29 to, what's the next date? 8:05. And then 8:06 to 8:12 8:13 to 8:19, and then 8:20 to 8:27. Let's say, yes, 5 weeks, and then that's it, 8:28 to, I think that's gonna be 9:2. Yeah, 9:2. So let's see. So first, we're gonna focus on your trees, your tree breadth first search, and depth first search. I really want you to hit these problems, and I want you to be able to do the associated grokking problems as well.
Okay.
So I mean, not grokking, but EPI, elements of programming interview. I think that's gonna do you some good. So that's gonna be chapter 10 for you. Binary search is also gonna be pretty good. So let's add that in for chapter 15. And I'll send this to you afterwards, but we'll fill this out week by week. But essentially, I think you might also benefit a lot from reading EPI. I think grokking and EPI is gonna be your best friends right now.
Okay.
So, that being said, let me look at your schedule. So, what is the how much amount of time do you put into this? What's your sleep schedule like? What do I need to watch out for?
Honestly, like after 4:30, I'm pretty much free.
Okay. So after 4:30, you're on Pacific Standard Time?
I'm on Central.
Central Standard Time, okay. Central Standard, I'll do this relative to you, and then I'll match up my shit. So
Okay.
you are out after 4:30, right?
Yeah, so I'm free anytime after that.
Okay, are you working a job right now?
Yeah, I'm doing an internship right now.
Okay, internship from how long?
It ends at the end of August.
Okay, end of August. All right. And what time do you wake up?
Usually like at 7:30.
7:30. Great. Okay, 7:30 wake up time. Wake up time. I'll give you 30 minutes for breakfast. 8 to 4:30 is your working hours, right?
Yeah.
Okay, cool. I'm gonna give you that. This is all your work. I'm just gonna highlight this because I don't know what the fuck goes on at your work. So after that, I'm gonna give you a 30-minute break in between that. So from 4:30 to 5, you are free to do whatever you want, relax a bit, because I know people need it. Check your email. Do you go to the gym or need anything else?
Yeah, probably like an hour and a half after work for the gym.
Okay. Do you think?
But that's only like 4 times a week. It's not every day.
Okay, I'm gonna say let's get. Okay, so an hour and a half. And then the thing is that I want to put your gym like when you need a break from studying.
Okay.
So let's do this. So I want to do you study for an hour and a half, let's say, or 2. You might need 2 hours. Let's start with an hour and a half because that'll be easier. So study will be here. And then what time do you eat dinner?
Usually like, I don't know, 5:30.
5:30. Okay, so then let's have dinner at 6.
Okay.
Dinner at 6. I'll give you 30 minutes. I'll give you an hour for that because I know you cook prep, but honestly, you can shave off time if you do meal prep and shit. 7 o'clock to 8:30 is gonna be let's see, 6:30, 7 o'clock to 9 o'clock. How long do you usually study for? Hour and a half, 2 hours, or what?
Yeah, I mean, I usually do hour and a half, 2 hours.
Okay. What time does your gym close?
It's 24 hours.
Perfect. So then if it's perfect, so then after that, 9 o'clock, I will let you take a break to go to the gym. And then hour and a half out. So then you'll return back home at 10:30, right?
Yep.
What time do you go to bed?
Usually like around midnight.
Okay. So we'll say midnight is your sleepy time. So then we'll put one more study session in here. So with that, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks. So that's like what? An hour and a half, 2, 3 hours. So it's like 4 or 5 hours. It's like 5 hours a day.
Okay.
So what I want you to do in each one of these times is I don't care how long it takes. You know, some of these problems might even take just an hour to do themselves when you do like trying to figure it out and log everything and try to figure out what to do better. I don't care. I want you to be very, very thorough about the efficiency. It's about quality time, not quantity. Okay. Yeah. So then we will do that. And then if you decide to do long term, we can talk about this offline. And we can talk more about it. But I'm going to give you the study schedule, at least how I would give it to anyone. Now, we will revise whether or not we need to adjust the schedule later on. But for now on, I think these are going to be your biggest 3 hits. Chapter 10, Chapter 15 of your EPI are going to be your greatest friends for the next few days. And I would hit these really, really hard, if at all possible. And then you can fill it in with some grokking, not grokking, but what's it called? Leak code tree problems in between. But I would say EPI is definitely a little bit more straightforward and it's a lot easier to handle. So.
Okay.
So knowing that, we have 4 minutes left. Let me recap. Let me write down the lessons I want you to remember from today's session. I want you to like look at the problem, start simple and small. You know, build up to the optimal solution. No magic bullets. And for that, I also want you to be patient. Be patient. Draw things out. Prove the answer, or at least the base case, the very basic answer, and prove that the basic solution works.
Yeah.
I also recommend rewatching this stream once it's done for the recursion tidbit. Because fundamentally, I think you're also very weak on this as well. Because all it is, recursion is just, you put shit in, you get shit out. It's a function, but it just calls itself. So, I want you to be able to really fully understand recursion. And with that, I think that's it from me. Let me share this with you. And then we'll fill out the schedule as we go. Because right now, I think I kind of know where you're going to have problems with. So, it will fill out later. So, here's your study doc. Alright. Anything else you need from me? We got like 2 more minutes.
No, I think that's all. Thanks so much.
All right, for sure, man. We'll continue this conversation offline. Let me wrap up the stream, and then we'll chat.
Okay, sounds good.
All right, for sure, man. Take care, man.
Yeah, bye.
All right, bye. All right. So, all right, let's answer some stream questions. Hey, Edward, did you recently start charging for these streams, or did I hear wrong? Yeah, so, basically, I have, like, a backlog of clients who really want long-term coaching. And that list is up to like 25 people right now. So it's like, in order to make it my time worth it, I kind of need to charge just because like the results that I get are so astronomically better than anything out there. I just need to make my time worthwhile doing this. But I do charge a very reasonable rate, and a lot of the clients, as you see, I do stream them for you guys. So it's not like I am completely shelling out, you know. I am also giving you guys free stuff as well. It's just that if you want targeted focus and my complete attention on your long-term success, then yeah, this is where the payment comes in. Hey, Edward, is the study schedule template public, or is that only for your coach? I usually just keep these around as like material for just to show people the way I really look at things and how I operate. I think that anyone can really come up with these templates themselves. Like literally, if you are serious about improving at lead code, interviewing, or anything, for example, you kind of need to do stuff like this. Have a schedule of like what times you're willing to be dedicated to certain activities, what you might be doing better, looking back at the problems that you do. So let me actually show you an example of the practice diary again. I think this is a super good. Like every single problem that you do should look something like this. Should be like you need to at least understand and acknowledge what you could have done better about the problem. You know, because if you just spam fucking leak code all day, you're not going to improve. You're not going to look at what you could have done better. You're not going to look at how you could have done the problem done faster. You're not going to do all that shit, so you're never going to improve. You know, this is why fucking people do 400 leak code problems and still fucking fail interviews, you know? I'm a very big believer that you can do 100 problems, and if you spend those, like, 100 hours it takes to really analyze those problems, you will be better than almost anyone out there. Like, literally, 99% of people taking these fucking interviews, if you actually just put some effort into trying to improve and think about like, oh, what are the insights that I need to do to build this up step by step, you will be doing phenomenally. There's no secret to this. It's just hard work and understanding that a lot of these magic problems or magic solutions are just simply building on very simple observations on top of each other and improving efficiency. I think I go over this a lot in like some of my videos. Yeah, sure thing, Sean. Thanks for watching the stream, by the way. I appreciate the audience, and it lets me know that there is interest in people watching how these things go and watching these coaching sessions. I think as long as people actively watch, participate, ask questions, and show an interest, I will continue streaming these. I have no problem with that. So, any other questions from the crowd? I guess I'll put on some Dota while I'm working on this, or answering questions to you guys. Oh, OG versus Nigma. Haha. Oh, that was a game. Actually, I want to watch that now that I think about it. Ooh, yeah, I remember this game actually. So yeah, I like this game. Entire game was like actually so good for Nigma. Like they were just tearing shit up. I think they actually, I don't know if they won this one, but like I remember them dominating the laning stage actually pretty goddamn hard. But then like Bushwhack I think saves the day or something. I think this guy like Bushwhack is like so giga farmed, it's unreal. Like I don't think Bushwhack should actually have this amount of farm at 25 minutes. Oh, it's a support. It's a core. Never mind. That's fine. They're playing behind the Morphling, and they're just gonna. I think they're pretty much losing all the lanes. They already lost their tier 2 tower here, and so I think Nigma is pretty much. No, OG is pretty much forced to play on this side of the map here. I don't think they're strong enough to really push this out until Morph gets like BKB or something. I think Morph only has like shotgun, so they're forced to farm here. Thompson's gonna be farming here, and then like kind of whoever farms here dies. So I think that's kind of the nature of things. And then here they don't have enough control either. So I think they have this ward here, but I think that until they see the Nigma heroes, they're not gonna actually farm here. Oh, never mind. Thompson's going for this while they're making a play mid. I don't know. This seems okay. Yeah, Thompson's joining them now. Sorry if I missed the guide. Do you have a question list? I'm currently doing leak code pattern 1. I don't really have a question list. If you read my guide, and I will link it, I think it's in the stream description, that if you follow that, I think you'll be fine for any interview, and I think you'll be completely prepared. Oh shit, that was a sick RP actually. They got Thompson though. I don't think they have enough damage to continue the fight. Yeah. That's a poor Morphling. You just get blown up by fucking Invoker. Yeah. So let me actually pull up the guide for you guys. Oh wait, shit! I'm missing the Kanye listening party. God damn it. So yeah, if you guys want to know like the guide that I use as a basis for how I do things, this is basically it. This is the document that lays out like how to basically study for all these problems and practices. So, Deep says, could you possibly go through your problem-solving method step by step, how to break a problem apart? I think I have a video on that already, actually, if you just go to my channel. And I think I walked through an example as well. Let me find it for you guys. So this is the full playlist. And then how to always solve leak code problems. Let's see. Why this? Yeah. So this video is going to be the one of me solving problems. Is this one? Hey guys, it's Edward. Usually occurs. So this one is just me basically laying out what's already in the guide. Like these optimizations and stuff. Yeah, so this is actually the high level overview of actually solving any leak code problem. So this is the high level. And then the next one would be this one where I actually walk through the actual problem itself. Log N. Yeah, so this is like me solving an actual problem. And then I think I have one more here as well of me solving problems. I think just watching these, and then you get another example. So yeah, I posted those in the chat for you guys. And so if you follow that, I think that you will be pretty much golden, actually. But yeah, that entire series I think is worth watching. The video is a little bit like, I would say slightly outdated, but the concepts still hold water. I think now that I have a better understanding of like what you guys need, I would say that a lot of the abstract concepts might actually go over your head. But for the most part, these are still very solid. In fact, this one is just how to actually study for coding interviews. You know, like I actually walked through this recursion thing for people. So, yeah. So these videos are there for you, and those will help you show how to break apart problem solving. But yeah, it's really just boils down to understanding what the key little components of your problem are, and then building up step by step, and then eventually getting to the optimal solution. That's really it. And I think I've demonstrated that today with the problems with Chris. Also, would you recommend doing different problem types or try to focus one type of question at a time? One question at a time, one different problem type at a time. Really, really dig into it. It would be really cool if you could do a mock interview with you as the interviewee and getting it over and going over it yourself. Yeah, I think doing that would actually be kind of cool. I could go to Interviewing.io and actually go do an interview. I think that'd be kind of interesting as well. I agree with you on that. Yeah, I think those are fine, actually. I think, yeah, actually, let me set aside a time to actually do that. I could do that on live stream. Why not? You know, I don't know what the... Well, actually, they don't tell me the results immediately, but I can actually maybe do an interview on live stream and then get the feedback and then do a feedback review and react to it on another video. I think that is a good idea. Just to clarify, should I try to avoid knowing the type of question before starting it? Yeah. I would say, well, at the very beginning when you're practicing, like when you don't know what the patterns or topics are, I think knowing the topic is fine. But after that, you should eventually get to a point of like not knowing. Oh shit. Yeah. Okay, does I think they give the Aegis to Miracle, right? Oh he whiffed the RP. Oh fuck. Ah, Magnus. No, that was not good. Okay, Morphling. Wait, Morphling got a link into this game? What? Oh, he doesn't... I mean, I guess his only threat is being swapped and sundered. I guess that's why. I still think BKB is better. But then again, it's like maybe he doesn't feel strong enough to win during the BKB time. And Diffusal fucks Morphling up so hard. Yeah. Okay, now he decides to go for the BKB. I still don't think they fight until they have a BKB, actually. I think the Ags gimmick is a little bit weird with the Willow. Like, I mean, if you're Morphling, who do you morph into? Like, just the Willow's the only one that really gives you power. Maybe you morph into the Terrorblade and then steal his Metamorphosis. But then it's like, what do you need Ags for? You only need Ags for the Willow and burst people. Yeah. So I don't know. I don't understand I don't understand the Ags pickup. Maybe I don't. But I'm not a Morphling player, so I'm not gonna pretend to know. Like, I think Sumail's like one of the best, if not the best, mid player in the world. But then he's like switched to carry. I don't know how he rates as a carry. I think he's pretty solidly, actually. Like, I still think he's really good. Like, maybe not the best. I think the best carry in the world is Ame, actually. But Sumail is definitely starting. I think by the time TI9 or TI10 comes around, Sumail will easily be top 3 or top 5. Like, very easily. That dude is a fucking monster. Okay. So, I see the questions kind of like slowed down and stopped, so I'm going to stop the streams here. Thank you everyone for watching the stream. Hopefully you guys enjoyed that. Hopefully we'll have like future streams with Chris and you can track his improvement. Oh, one more question that just came in. Might be a stupid question or repetitive, but as a beginner who wants to learn programming, which language would you say is most beginner friendly or important to learn? Really anyone. I would say Python's the easiest to pick up because you don't have to worry about a lot of things. But once you really learn one programming language, you know all of them. Like, there's no reason to have to learn 3 or 4, you know? So just pick one, stick with it, and do good shit with it. So just to wonder, how much is the long-term coaching? The pricing varies depending on level, experience, and I usually negotiate with my clients on that. If you want more, you can just go to my Discord channel and ping me directly about rates. In fact, let me link to you guys I think the link should be in the description of the stream. Yeah, the link to the Discord is in the stream. So, you guys really want, just ping me on there, send me a message, and then we can arrange something. So with that, have a good night, guys. Thank you for watching. And hopefully we get to see Chris next week or sometime. So, catch y'all later.